Okay. Okay, yeah, properly recording now. So yeah, today, diodes, LEDs. I'll be going over the four main diodes, being the general purpose, the most common LED that diode that you'll kind of encounter, jockey, Zener, and TVS. They all basically have the same purpose. They do the same task, but they all have a slightly different characteristic about them, different benefits in certain areas. So we'll go over what those may be and why you would use one over the others. So starting with just your general. Symbol is as such. Now the point of kind of all diodes, the general kind of function of them, is that they only allow current flow in one direction. And block in the reverse direction. So no, you can't have any backflowing current. So this is good for simple reverse protection systems. In such cases where you want your normal operation to have current flow coming in, so you would place a diode like so, and then the rest of your circuit. And then in the event that you mess up and you place your battery backwards, it would block any current flow from coming back through the diode, so you would have a open circuit at this point, so you wouldn't have any current flow and you wouldn't be able to destroy your electronics through a short circuit. Now the general characteristics of a diode being that they cause a voltage drop, or they have a forward voltage, turn-on voltage of forward voltage of, most generals are 0.6 to 1.2 volts typical. So that means you have to apply greater than the forward voltage to turn on, and you'll see that voltage drop across. So you have some VF equal to 0.7. So your battery has to be greater than 0.7 to allow any current flow across. And then once you apply some voltage greater, you will see the voltage drop across the diode, and you'll have only, say, 4.3 volts on the output. Now this is why we saw last time with the terminating resistors, why you couldn't use a diode for that same case, because you would have a voltage drop of 0.7 to 1, which can mix up your logic levels. So you wouldn't want to use it in such a case where the voltage level is required to meet any of the backflowing requirements. We can also do that up diodes in series. So if you wanted to require a larger turn-on voltage, you could put two diodes in series. That way it requires either a larger turn-on voltage, or you could do it in the event that you want to cause a known voltage at the output. So if you have two at 0.7 and you input your 5 volts, you will know that you get a 1.4 drop across. So you can do it in that case where you have a known voltage drop going across, and you can have a steady voltage output at that point. It's not the most efficient way to do voltage dropping, and it's not always the most reliable, as 4 voltages aren't precise across diodes. But that's one use case of them.
I have a question.
Yes.
Is there any reason you would use the diodes in this case instead of a resistor?
No, not really. It's, geez, there is a purpose for them. It may come down to current. As if you were to put resistors, if you were to have a resistor in line to create some voltage drop, you lose more heat in the process when you use resistor, whereas the diodes have a lower forward current drop or current draw. So in that case, you could have a higher current at the output on the diodes, just depending on the whatever resistance value V equals IR, like we went through last time. I'm pretty sure that's one point if current is a very important feature that you're requiring. But I think there's better ways to get around it, and it's not, diodes still aren't the best way to go through about that. Now, there is a case of diodes where they will allow current to flow in the opposite direction. So if you apply a large enough, a large voltage on this side of the diode, you will be able to break through and cause current flow across the diode. This is known as the reverse breakdown voltage. This value is typically on the general purpose diodes that are typically a few hundred to 1,000. They can range on massive values, and they're not overly predictable. So they're not designed in any way to work in the reverse breakdown region, unlike some of the other diodes we'll touch on. So they work well for allowing current flow through the diode as proper, and then if you apply a large enough voltage, you are able to break through in the reverse direction, but it's unstable and not a precise read off of the actual in a usable range. Any questions on the general purpose?
once you go through the reverse breakdown voltage, is that diode busted or like is it still fine?
It, as long as you don't actually exceed the voltage rating of the diode, if you just hit the reverse breakdown voltage, I'm pretty sure it's able to recover. So if you were to drop the voltage and run it across proper, it still functions with some degradation of its quality. But I'm pretty sure they are able to work if they're brought back to the proper rating within their proper operating range. Anybody else? Anything on the general?
What happens if two currents are flowing in opposite directions but simultaneously? Will that opposite current be allowed to flow?
If you're running two,
just from reflection, or any other way where there's just two currents simultaneously?
oh, so if we're talking in the case of you're properly sending your signal, say, across, and then we have the little bit of noise bounce back.
Yeah, will that go through?
No, because in the case of when we're talking, like if we were talking about this bounce back, the signal strength of your bounce back is going to be far less than your actual input signal. So it's not going to leak back in. It's more of a matter of it'll just distort at the node or fully just be blocked off. It's not like a gate where it's once it sees a voltage here, it closes and allows anything to flow. It only wants to allow forward flowing currents.
Okay, thank you.
Cool. So can you use a diode to reduce like some noise coming back to wherever you're sending the signal from?
Technically, yes. Like it is capable of doing some filtering out some any like bounce back signals. But the problem why you wouldn't want to use this is because you see a voltage drop across the diode. So although it will get rid of this bounce back noise, you lose your top end. Instead of having a clean 5 volt to 0 volt, it'll drop down and it'll become, once it goes through, it'll become a 4.3 to 0 volt signal. But it would be able to stop any bounce back interference.
Okay.
One big use case of the diode is a rectifier. That is where you have 4 diodes. Did I do that correctly? No. Jeez, why can't I remember what a rectifier is? KBL out. Do I have this drawn?
Yep. Like the AC goes on the top and bottom, and then you steal the DC from the middle. But your top right diode should point the other way, and your bottom left should point the other way. as well.
That's what I thought.
Yeah, it's like a little path.
Yeah, so you send you'll send in AC, and then you'll read DC across the center load. Because as you send AC through a diode, since it wants to block any negative voltages, your output will get chopped. So as you send a sine wave through the diode, it'll see the positive voltages and allow it, and then once it's seeing the negative voltages, it'll just clip it 0 and return, and it will carry on. So in the case of the rectifier, when it's on its positive half cycle, pumping current in, you'll see current properly come across, and then it gets blocked by this diode. So it comes across your DC load, then signal path, and over to ground, and completes the path. And then on the negative cycle, which is on the negative sine wave, current will come flowing through, and again across in the same direction, and complete its path. So your output, instead of seeing a clipped sine wave, it'll see rectified, so your negative half cycles will come up, and instead your output will become a very unfiltered, just all the negative cycles come up, and you'll have a bunch of positive half cycles. This can then further be filtered to get a smoother kind of DC output from an AC source. This is the simplest setup of an AC to DC, and we can go over that in another lesson on power conversions.
Does the flat part of the rectifying thing, does it matter? Does the forward voltage matter? Does it exactly flatten out when it's at 0, or does it flatten out when it's at the forward voltage?
At the forward voltage. So yeah, if we were to you'd put a nicer photo of a rectifier. But yeah, so if we have our sine wave, and we say 0.7 is here, what we'll see is nothing, and then nothing. So it does clip at the 0.7. So once it actually passes that threshold, then it follows the sine wave. And then again, once it hits under 0.7, it goes straight down and clips it.
Okay. Thank you.
Other questions on the general purpose? Okay. Then on to the next one, the Shocky. Which now has as slightly varying symbol. Functions basically in the same format as the general purpose. It only wants to allow current flow in the positive direction. However, these have a lower forward voltage compared to the general. Being on the scale of 0.1 to 0.4 volts opposed to the 0.6 to 1.2 volts. So these can be better in lower voltage applications, where if you're only dealing with, 1.3 to 3.3 volts, like if you're on that sub 5 volts kind of area where you can't really afford to be losing much of a voltage in your signal, the Schottky is what you would go for. It's primarily, its main spec compared to the general is the lower forward voltage, but they also have a much lower reverse breakdown voltage compared to as well. So your reverse breakdown voltage is also going to be in terms of like 40 to 100 volts, whereas the general was able to withstand a couple hundred to 1,000 volts. So these aren't suitable in high voltage applications if you're trying to block reverse voltages, or if you're trying to make a high voltage rectifier using Schottkys. They will break down, at 50 to 100 volts, so they'll become null and cause short circuits in your system. So they're better for the low voltage systems, especially when you're going about wanting low voltage drops in your system. Other than that, they have all the same functionalities. Block as they want, only allowing forward voltages. I don't have an actual system application using the Schottkys, but they're fairly similar to the general, just at a lower voltage ratings. So that's basically all I have on this. If there's not a question on the use of a Schottky. No? Okay. Third one, the Zener. This one is where we start to get a little different from the other diodes. This one, it allows current flow in both directions at a predictable range, whereas the above ones, they preferred to be in the forwards. In a forward bias, they only wanted in the positive cycle. Zeners will allow a reverse breakdown at a lower voltage and a much more predictable voltage. So they allow current flow in both directions. The forward voltage is roughly the same as the general. So that's 0.6 to 1.2 volts, typical forward voltages. So again, once you bypass so again, they will, once you get past that 0.7 or whatever forward voltage it'll allow, and then they have they will have a same reverse breakdown. At a couple hundred, like the general purpose does, but they also have what's known as the Zener voltage. And this will happen depending on the diode, depending on the diode you have spec'd, can be 3 to 100 volts. The thing about this Zener voltage, or -3 to -100, is that it's a very predictable breakdown voltage. So unlike the actual reverse breakdown voltage, which is inconsistent and will happen at a larger range, the Zener voltage will happen at the rated voltage. It'll allow current flow in the opposite direction. So if you were to apply, if we were to say this has a Zener voltage of -5 volts, you would know that as soon as you actually have 5 volts or greater than 5 volts applied to this end of the diode, it would allow current flow in the opposing direction. So this diode is often used for voltage limiting in cases where you have your load, and then you would have your Zener before going into the rest of your circuit. So if we were to call this a 5 volt Zener as well, it would allow current, it would block any current flow as long as this is less than 5 volts. If your system, the rest of your circuit on this side is 5 volt tolerant, and then as soon as you were to apply 5 volts, the current path would then be across the Zener, and you wouldn't get any current flow into the rest of your system. So it's typically used for voltage cutoffs in systems, whether it be for voltage tolerant pins or components in your system.
I have a question.
Yep.
So if you hit over 5 volts on the Zener diode, is the result of that like a short circuit, or does it have enough resistance to allow the current to flow for a long time, or how does that work?
Yeah, so it does have some internal resistance, so it's not causing an actual short circuit here. I would have to pull up a data sheet to actually figure out the numbers, because I don't have that actually checked out beforehand. But yeah, when it breaks down, it doesn't cause a direct short circuit, so you're not going to then damage the system that way.
Okay, that makes sense.
When it goes the opposite way, like the going down in the middle, does it still have a voltage drop, like the same as the forward voltage?
Yeah, so it has the voltage drop of 5 volts. So in the case that you apply, it does cause a 5-volt drop across the zener. In this case, in the same way that when it conducts properly in the opposite direction, it would cause a 0.7 drop across.
Mm-hmm.
So if you were to apply a, say, 6-volt signal at this point, you would see a 5-volt drop.
Ooh, okay. Great, thank you.
Have you used it for anything other than protecting from like over voltage?
I have only seen it in voltage limiting cases. I haven't seen it in any other applications. Maybe Gabe has.
Over voltage is the most common, especially like on microcontroller pins where you don't want to blow it with too high a voltage. Some people like to use them as like crappy voltage regulators because it'll clamp your voltage to a certain level. And so you can like use like 24 volts and then send a resistor and then a Zener diode, and then it'll clamp it to 5 maybe, for example. But then that burns a lot of power, so it's not the best. But usually it's whenever you want to clamp some voltage. So over voltage is the most common.
Yeah. Just to let you know, like some teams they even use the Zener diodes as for the T sound, like instead of the LDO.
Yeah.
Yeah, but they burn a lot of power, so it's not really recommended. So.
Yeah, I remember Koi talking about that once. But yeah, it is definitely not the best way. But super useful, used everywhere. It's on the VCU, it's on the BMS. It's a very common thing.
So primary being the voltage cutoff, useful for protection. Any other questions on it? No. Okay. Then on to the final diode of discussion, the TVS. The TVS acts similarly to Zener. It also has 2 variants, being a unidirectional and a bidirectional. Now the difference to the TVS compared to a Zener is that the TVS is for transient voltage suppression. As the name implies. So it'll do the same. It does the same kind of aspect as the Zener, where once there's a voltage greater than what it's rated to, it gets clamped, so the current path goes through the diode instead of the system. However, it is more used to suppress the transient voltages, which are the instantaneous voltage spikes that may be upwards, that are magnitudes above the actual voltages that are seen in your system. So this can be seen in square waves, sine waves, or ESD. As we discussed last time, square waves aren't perfect. There is some ring to them, so they'll have some undershoot, and then they'll come up and have some overshoot, and then they'll do this a bunch. So these peaks are capable of being several magnitudes above what your expected voltages actually are supposed to be. Or in the case of ESD, or electrostatic discharge, which can be a few thousand volts, and can come from just human touch. If you're just touching the pins, unprotected, ungrounded, if you were just to go up and poke a pin, you have enough static charge in you at times to potentially short or induce these high transient voltages into your system. So you can cause these peaks and destroy your system. So TVSs are used to combat these. They're used in the same way as a zener, so they'll clamp at that excess of voltage, but their breakdown voltage is much higher than the zener, so their reverse breakdown is going to be a few hundred to a few thousand plus volts, so that they're able to withstand these high transient, high discharge voltages. They're also more commonly they're used in their bidirectional state for AC signals, so that it's able to withstand any possible spikes that happen in your AC signal from ESD or whatever may have caused. So it's able to clamp any positive as well as excessively negative voltage spikes without damaging your systems. These are typically used on input pins, communication pins. So you'll see that anywhere that you would be plugging in, so USB ports are major for this. You'll have whatever your USB port. You'll have your plus and minus pins, and then you have the 3 data pins. Typically, you'll see these 3 pins will then all be tied. They will have some TVS, like some discharge diodes going to ground. Since this is the USB ports and other ports with human interaction, commonly have reduced with voltage spikes, just because you're able to transfer from that point. You'll often see these lines have TVS diodes or other voltage suppression tied to those pins. Questions on that? Nothing?
Is it the same as ESD?
Yeah, so ESD is just a form of transient voltage spikes. Because in all ESD is inducing high instantaneous voltage unexpectedly into the system. It's the same thing as any noise interference causing that voltage spike or other systems like that. So the TVS is what would be used to reduce those spikes. Any other questions on? Okay, so the curves you'll see associated with diodes are current and voltage. So you'll see at 0.7 volts, so if this is your general, and then at some couple hundred, you'll see that for the most part of in the negative region, it'll allow no current flow. And then past 0.7, it's free to conduct as much current as it wants to. And then if we were to look at the Schottky, it happens a little bit sooner at 0.3 and will die off a little bit faster, 70. The Zener, typically same curve as general, but then has a much lower and predictable. And then the final TVS will have the same, roughly, but then will break down at the higher end of, again, several hundred. The thing to note is that the Zener and the TVS, these are much more predictable and much more stable breakdown voltages. So when they are rated for a Zener voltage or breakdown voltage of 5 volts, you know that it will more or less accurately break down at that range, whereas the breakdown on the Schottky and the general are a little more unpredictable. They won't happen exactly at their rated breakdown, or their breakdown voltages have a much larger range on them. So when reverse, so that's why you would use a TVS as opposed to a general, even though they may break down at the same few hundred. The TVS is going to be more known to actually suppress at that level. Everybody good on diodes? Yes.
Yeah, all makes sense so far.
Good. Okay. Then the end of it. LEDs, which essentially the same thing. They're light emitting diodes. So they have the same characteristic. They have nearly the same symbol. Still a diode, but a couple arrows coming off. So they have the similar characteristics. They have a forward voltage drop of roughly this will change based on the color of LED that you're using. It can range 1.8 all the way up to 4 volts. That's depending on what color of LED. So I believe your red LEDs have a lower, and then it goes up to your whites, and blues will have the higher voltage drop. But it has the same effect as the normal diode. So once you apply enough voltage, so you get over the forward voltage, current is allowed to flow through the device, and you get some light. The thing to note about LEDs opposed to general diodes is that they also have a current limit. So your typical LED will have a current limit of 20 to 30 milliamps is typical. So unlike a diode where once you get past that voltage, it is freely allowed to just allow current flow through. With an LED, you have to have some form of current limiting in your system to not exceed these current limits. Otherwise, you're going to instantly, if you were just to apply some voltage to your LED, even though maybe this is only 1.4 volts and this only takes 1.2 volts to turn on, because you have no current limiting, you'll just fry the LED and you'll toast it. So this is where we use resistors for the current limiting aspects that they have that we went over last time. So if we say this is a LED that has some forward voltage of 2.1 volts and it has a current limit of 20 milliamps, and we have a 5-volt source, we know we have to spec this resistor to only allow 20 at 5. But to properly do this, instead of just having it be your swap it around and do 5 over 20 milli. This is wrong because you have to take in consideration the voltage drop that the LED imposes on the system. So the true system is you take your whatever input voltage minus your voltage drop across over the 20 milliamp current limit that you have on the device. And in the end, we can find that we need 145 ohms or larger to be able to properly run this LED. Now this 145 should be taken as the absolute minimum. If you were to go in and you only have 140 ohms and then 150 ohms and then carry on, it is much more recommended that you go with a higher resistance so that the current that it produces would be lower. So if we were to keep this 5 volt, 2.1 volt system, we have a 2.9 volt, and then take that over our 150 ohm, you'll get something that is slightly less than 20 milliohms, which will keep your LED in the safe, usable area. Because if you were to drop it to 140 ohms, we would get something just slightly over 20 milliamps, and then then you're able to possibly damage your device, the LED, that way. While they are capable, like they have a maximum limit, sometimes it's 40, 50 milliamps. If you use LEDs above their rated current for a duration of time, you start to degrade them quicker. So the color will go a lot faster and they'll eventually burn out faster compared to if you're using it below their rated current limit. So although it is possible to get away with having an increased, a decreased resistance and an increased current limit, you'll get it brighter, but it'll die out faster. Questions on that so far? No?
To get a range for the resistor you want to get, do we just look at the current limit range and just calculate it from that?
Yeah, so if you are to pull up a resistor, pull up an LED off DigiKey, you would see right away they tell you what the forward voltage is and the current limit, which is almost always typically 20 milli for standard LEDs. Yeah, you would do this and you would find 145 would be your absolute minimum. And then you can go up from there. So like if you don't want to be at the absolute edge because maybe you don't have a pure 5 volts, maybe it fluctuates, maybe it's 5.5 volts. So that would be enough to tip it beyond what it wants to. So you could do a safety factor, maybe make it 160 ohm. But you'll be able to see at that point, you'll be able to run through the calculation again saying, okay, so this is the minimum. Maybe I want to do 170 now, 170 ohms. See how that acts. You'll see the current through the LED will drop. So your current LED will go down, which makes it so brightness goes down. So it'll definitely be able to last, and it'll be a little more stable. It'll be able to withstand minor fluctuations in your input voltage, but you lose some light intensity.
Okay. Thank you.
Now, if we are to have multiple LEDs in series, you can have LEDs of different colors, so they will have different forward voltages. So this one may still be at 2.1 and at 20 milliamps, while your second may be somewhere higher, 3.2 volts at 20 milliamps. Now it's possible that it's preferred if your LEDs have the same current rating if you're throwing them in series. But in the case that maybe this one is actually rated for 30 milliamps, you would still want to spec your design to only allow for 20 milliamps, since that is that will be the more limiting factor on the design. If you design it for 30 milliamps, you'll instantly blow up the red one, and then the blue one would be able to operate, but obviously you've destroyed your design at that point. But the logic still follows, so it's Vn minus a voltage drop minus the voltage drop all over your limiting current. So again, if we obviously now we can't just give it a 5 volt input because the combined voltage drop is greater than 5 volts now. The total voltage drop across the LEDs is now, what is it, 5.3 volts. So we have to be able to supply something greater than 5.3 to be able to actually run the two LEDs. So let's say we're giving it 12 volts. So we can do not the same at 20 milli. We can spec 335 ohm. So again, this is the absolute minimum value that you should be going with. It is preferred to go higher just for the safety factors. And yeah, if we're to, this one maybe does have a limit of 30 milliamp. You still want to run the design at a 20 milliamp, just so that the overall system, since it's going to fail at 20, design it at 20 instead of going for your upper limit. Makes sense? Everybody, yes? Any questions on this? No?
Do you have any other things, Jarod?
This was it. I'm going to get you guys to actually do an LED resistor calculation.
Yeah.
Nice and
Yay.
very challenging.
Do we get to pick our own LED on DigiKey?
We can go through pick your own LED, or I can send. I can pull up an LED and make you find the values.
Or do people want to do more?
I think if we just send one, it'd be easier because then we'd all have the same values. It'd be easier to check.
Okay. I'll pull up an LED and I'll get you guys to search through, find the current limit, find the forward voltage, assume a 9-volt supply, and we'll see what you come up with.
Jared, I actually have a question.
Yes.
Is it possible to have LEDs in parallel?
Yes.
Would it still be the same calculation?
If you're doing it in parallel, so yeah, if you have your, so if you have your whatever VN, you would go through some resistor into LED, and you would go to some you wouldn't want to just put one resistor at the beginning and then nothing through. If you're putting them in parallel, you want to limit the current on each path, so you would place a resistor in line on each one. But then, yeah, so the equation would follow. It would be the same thing. So you take it as, so for path 1 and path 2, it's going to be the same. Vn minus your voltage drop of 1 over your current limit. And then same thing, no changes, just your voltage drop across to current limit. So it gets simplified. You just do it as 2 different equations.
Got it. Thank you.
Okay. Pull up an LED. Okay, everything. So we have a white LED data sheet in front of you. Everything you need can be seen right from the front page of this data sheet. So let's assume we're taking a 9-volt source. Everyone figure out what the resistance we'd want on this is.
Could you write those numbers in the chat or something?
No, why don't you find the numbers?
But like I don't remember exactly what I said, the 9 volts or...
Okay. Let's... So we have some 9 volts, some resistance R that you're trying to find. Through this LED. Everything you need can be found on that page. Do we have some answers?
Is it 400?
400? No, not quite.
To just say our answers?
Oh man.
If everyone has an answer, we can type it in chat once you have it. Maybe give it a minute once everyone actually confirms we have an answer. Okay. Yeah, so does everybody have something by now? Gave your child.
I got it right.
We have 16, 800, 580, 61, 900, 69, 420, 100.
420.
I cannot type. What the hell?
Then what's your answer, Koi?
Oh, yes.
Okay, so what did we find as forward voltage?
.9 volts.
What'd you go with?
2.9.
2.9?
I use 2.9 as well.
Yeah, so we have your 2.9 volts. So whatever, 9 minus 2.9. And our current limit?
10 milliamps.
10? Yeah. Everybody properly see that? 2.9 and 10 milliamp is what we're supposed to be using in this case. Now it is possible that we could have been considering 2.9 at 5 milliamp. But that's but the number we generally concern with would be in the max readings. So we don't overly care about the 5 milliamp value. So then, yeah, whatever, 9 minus 2.9, 6.1 over 10 milliamp. What's that, 16?
Did I get it?
It's pretty close, okay?
I think
So
I was
close.
close. I think, did only Elena get it?
Yeah.
Oh, nice.
By a
Based,
factor of 10.
based on chat.
Damn it, Braden.
Yeah, so to everybody that didn't, using other values, we're just
Why wouldn't we use the 40? Why wouldn't we use the 40 milliamp value?
the 40 as your current?
Yeah.
Because that is the absolute rating for peak pulse current. So it's only able to withstand this 40 milliamp for a 10%. So for 1 millisecond, it can withstand this 40 milliamp. But if it were to sustain that 40 milliamps, it would just burn out the LED pretty quickly. So that's why we don't use the pulse current.
What does that duty 10% mean?
Duty 10% or pulse with 1 milli. That is a great question. 10% pulse width. So it's actually less than a millisecond, isn't it?
It's unclear if they mean the positive pulse is 1 millisecond or the whole period. I'd say the positive pulse, but maybe you can draw it out so we know what it looks like. Yeah.
So yeah, when they're talking duty cycles of some percentage, it's the on time of the entire cycle. So from edge to edge is your entire duty cycle. So if we're only on for this small sliver being 10%, and they're saying the pulse width 10% equates to 1 millisecond. Yeah. But yeah, so that's primarily just saying only for a short period of time, which would generally be during startup, that you would see a possible higher spike of 40 milliamps, based on the ringing effect that we stated, that we've seen before in any square wave, that it'll happen overshoot. So that's just saying it's tolerant to allow some peak for a short duration. Mute Koi. So yeah, any question on that for those who didn't get the 610? Is it clear now as to why?
Yeah, it makes sense now.
Yeah, so for LED, almost all LEDs, you'll be able to find the values that you actually need just from the very first page. Take it as the forward current of whatever, and then you'll be able to find the forward voltage. And you generally want to go with the typical values, because that is its nominal. That is what it's most likely going to cause as a voltage drop. So the what you go with is right off the front page. Those two values is basically all you'll need to do to be able to find your components, to spec your resistance and such.
I have just one question.
Yep.
For RGB LEDs, how does that work exactly? Because the forward voltage would change depending on what color you're shining it at, would it not?
Yeah. So RGBs, they're generally multi-legged devices. So you'll have a device that has your three packed within. So this will be your physical package of the device. You'll have your RGB, and then typical, depending on common anode and cathode, depending on which device it is. All the cathode will tie it together, or anode, sorry, and that'll just tie to ground. And then you would plate, and yeah, they'll all each have their own forward voltage across each other, and potentially all will have a different current limit as well. I think they're generally spec'd in such a way that it's consistent, but you would apply a resistance to each their own pin, and then maybe that would all tie up to one. So it's essentially like having 3 LEDs in parallel. So they won't directly impact the other based on whatever their voltage drop is. But they'll all need their own resistance resistor associated with it to get the proper spec values.
So each of the 3 resistors is likely different, so that you can match the currents through them and get equal brightness.
Yeah. So if they're all say all the currents are equal, but forward voltage 1 is at 2.1 volts, your green is going to have 2.6. They're all going to need a slightly different resistance to be able to have those all take in 5 volts but properly output 20 milliamps, or whatever the actual current limit is. But yeah, you can basically treat a RGB LED as several in parallel. Any other questions on any of this? Someone that hasn't said anything the entire time? This is all still making sense? Justin, Raphael, Alexis? Pretty fully fine? this is all I had for today's lesson. Went through it all, diodes, LEDs. So this is basically it for today. If it's on anything that we covered today, on any of the diodes, any of the LEDs, speccing, where to use, what to use, any of that. If nobody has anything else, that's basically it.
Coolest beans.
Yeah.
Thanks,
Thank
Jared.
you.
Thanks, Jared.
Thanks, Jared.
Very nice.
Thanks, Jared.
Sending love.
Yeah, so that's basically it. We'll have next one on next Tuesday. We might do Tuesdays at 5:30, if that's fine with everybody, just to allow the other sub teams to also get their meetings in at a reasonable hour. So probably 5:30 on Tuesday. We'll go over what did I say? Inductors and snubbers.
Will other teams be starting lessons next week?
Probably not. Matthew, Mahmood, do you have insight onto when you guys are starting the other team sessions?
I don't think we're gonna have lessons for embedded. Ready?
You should, Mahmoud.
I don't know. We'll see.
It'd be pretty interesting.